Okay, for today, we're going to continue our lesson on distillation efficiency, or also known as tree efficiency. So we have 5 subtopics altogether. Okay, so the first one is the distillation efficiency. Right, so in the previous discussion, we assumed that the vapor leaving a tray was in equilibrium with the liquid leaving. So, however, if the time of the contact and degree of mixings on the tray are insufficient, okay, the stream is actually not in equilibrium. So if you recall, okay, when you are using a two approach to calculate the number of stages n, okay, that's actually refer to the ideal number of stages. Okay, whereby we assume that the vapor leaving a tray was in equilibrium with the liquid leaving. Okay, however, okay, in real industry, okay, usually the tray efficiency will not be 100%. So this means that we must use the actual trays than the trickle number, okay, determined by the calculation. Alright, so here is three type of plate efficiency that we need to know, okay, which is the E0, EM, and EMP. Alright, so I want you to go through by yourself and read the definition. What is the E0 here and the equation here, the EM and also the EMP. Alright, so for the EM and EMP, it's better for you to refer to figure 11.5-1 inside the textbook for you to understand the location. What is the location? Where is the location of this yn plus 1 and so on. Alright, so look up to the subtopic here, okay, which is the relationship between the trade efficiency. Alright, so we have, okay, when the EM is known, the E0 can be related to EM by several methods. The first one that you can see here is the analytical method or the equation. Alright, whereby here the M represent the equilibrium line. Alright, and the L over V represent the slope of the operating line. However, to use this analytical equation, it is only limited when the equilibrium and operating line is a straight line. Alright, so in most cases, the equilibrium line and the operating line is not a straight line. So in that case, okay, we are using a graphical method. Okay, so straight away okay, this is the relationship between the trade efficiency. If you look out here, okay, this equilibrium line, the one that you plotted before, okay, so here we have what we call here right now is the ideal equilibrium line. So you can see that we still have a 45-degree line, and we also have an operating line combining the enriching and stripping line. So right here you can see that you have a dot line here. So this dot line represents the actual equilibrium line. Okay, so the way you want to calculate the actual number of stages, okay, the step is similar. It means that you need to step off, okay, from the operating line into the actual equilibrium line. So you can see here, as the actual equilibrium line is approaching the operating line, that will give you the number of stages much bigger compared to the theoretical number of stages. So if you can see here, the triangle ACD will represent the ideal plate, and the triangle ABE will represent the actual plate. Alright, so the correlation is for EM. Alright, EM is actually the AB over AC, which is the length between the operating line to the actual equilibrium line over the length of operating line to ideal equilibrium line. Alright, so straight away go to the example here. So this example is actually a combining problem of 11.4-2 and 11.5-1. Alright, so here, okay, stated inside the question, a saturated liquid feed, we have 200 mole per hour, and given to you the operating pressure, okay, the SF is 0.42. and the reflux ratio is 2.5. So extracting the data here, okay, so we have all the information given. So the question A is quite straightforward. okay, you just need to solve this simple mass balance, the overall and component mass balance, in order for you to find the value of D and W. Alright, so for looking for n, number of theoretical tray here, or number of theoretical stages. So here is the 5 step. So the first one, you plot the equilibrium line as usual. This one is given inside the question. Alright, so you can plot the you need to develop first, okay, the enriching line by using this equation, and then that will give you a graph. All right, so you can see here, this is your y versus x, and here is your 45-degree line, and this one is the ideal equilibrium line. Alright, so if here is a Q line, because the feed is in saturated liquid feed, so you just plot a straight vertical line at SF, which is equal to 0.42. Alright, and then here we want to, okay, so we already plot, so also this one is the operating line, okay, combining the enriching line and also the stripping line. So right now we want to focus on question B. The question B, okay, asks us to look up for actual number of stages if EM is 0.55. So what you're going to do here by using the graphical approach is, you know that the EM is actually the AB over AC. Alright, so distance AC here, okay, I write down the distance, the definition of the AC and AB here. So right now, straight away look out into the graph here. Okay, let's say at point 0.6. Okay, at point 0.6, you take your ruler and you measure what is the distance between the operating line and also the ideal equilibrium line. Okay, so that will give you the value of 0.8 cm. For example, okay, according to my graph. Okay, so to plot AB, okay, to find a point for actual equilibrium line, you need to multiply the 0.8 with the EM, okay, and that will give you the value of 0.44. So what you're going to do is that you take your ruler, okay, so you need to measure the what is the point of 0.44 from the operating line, and that will give you some point here. Okay, let's say point X here. So here you need to look up for several, repeat the same step, okay, for several points, let's say 4 to 5 points. So here in my case, I look up for 5 points here from 0.1 until 0.8. So you can see that actually you should be able to plot you plot actual equilibrium line, which is between the operating line and also the ideal equilibrium line. So in order for you to find the number of stages required, okay, you just need to step off, okay, starting from the SD here. Okay, the step is similar. So you can see that actually the number of stages will increase. Alright, so after you're done, okay, calculating the number of stages from the XD here until the XW, alright, it will give you the number of stages is about 70 stages, which is representing 16 actual stages plus rebroiler, and the feed on the stage about 8 to 9 from the top. Alright, so that's how actually we are plotting, how you're going to plot a graph for a line for a actual equilibrium line. So the question C, you need to find what is the overall efficiency. So you know that the overall efficiency is a number of added tray over the actual tray. So for question A, alright, you know that you have 9.5 stages, so just divide it by 16, and approximately it will give you that the E naught is about 60%. Okay. That's for the first part. Okay, now we straight away go to the efficiency of random packed and structure packed tower. Alright, so this is the HETP. So you know that the definition of HETP is the height equivalent to a theoretical plate. Alright, so in order for you to find for height of packing, okay, means that how tall your column will be. So this is the equation that you're going to use. And if you're using the number of transfer unit, this is the equation that you're going to use. All right. So for tray tower, the HETP can be defined as a T over E naught, where E naught is the overall tray efficiency and T is a tray spacing. So that's why it's stated here, in order to design the number of tray, all right, the efficiency must be obtained. Because once you know the efficiency here and you know the tray spacing, we can calculate for HETP, and eventually we can calculate for a height of packing, which is how tall our distillation column will be. Alright, for the estimation of efficiency, alright, we have three equations here. It's for either for the tray tower, random pack tower, and structured pack tower. Okay, so you can refer to the example 11.5-1 here. Inside the textbook, it stated that a liquid feed of benzene toluene is being distilled under the same condition. All right, and so that we just take out the information from there. So the number of stages required is 7.6, SF is 0.5, and okay, this is the information. Okay, so right now the first question asks you, alright, using the valve tray, okay, or tray tower, calculate the E naught and the tower height, assume that tray spacing is 0.6. So I write down here the equation that we're going to use to solve this problem. Okay, so the first one is for the tray tower, you know that is the equation. We can calculate the E naught from this equation. And since the spacing of T is given 0.6, we can straight away calculate for HETP. So once we calculate for HETP, we can calculate the H by multiply the HETP and N here, right? Alright, so N is 7.6 in our case. Okay, so looking here, okay, here information given. So right now, in order for you to calculate for E naught, you need to have the information of mu L and alpha. Okay, so mu L here, the definition is the viscosity, okay, at the liquid feed at average tower T of the top and the bottom. So first, you need to find the average tower T first. Okay, you need to find the average tower T. Okay, and how you're gonna find it is the first one, you need to look up for the boiling point and dew point from figure 11.1-1. So for our case, at SW0.1, that will give you the T boiling point of 106.5, and at D0.95, this will give you this respective value of dP, and that will give you the T average for your column is about 94.4 degrees Celsius. So you need to look up what is the viscosity, okay, of the benzene and toluene at this specific temperature at 94.4 degrees Celsius. So to look up for recipe here, okay, you need to use, you need to refer to the table A3-12 and also refer to the figure A3-4. Okay, so if you look at the table A3-12 here, okay, there is some actually a coordinate given for X and Y value. So we just extract the information from there. So for the benzene is 12.5 and 0.9, and toluene is 30.7 and 10.4. Okay, so by looking this, by using this coordinate, okay, you need to use figure A3.4 here, A3-4 here. So here is the figure. So it's actually quite a unique graph, alright, because you can see here that you have the y-axis temperature and the right hand side is the viscosity. So let's say that you want to look out for viscosity of benzene, right? So you need to find this coordinate 12.5 and 10.9. Okay, so 12.5 and 10.9 should be somewhere here. So what you're going to do is that, let's say here, okay, you have a temperature of 94.4 degrees Celsius. So make a straight line from temperature touching this coordinate and then bring it to the right hand side. So here that will give you the value of the viscosity. Okay, so from here, okay, the viscosity of benzene will get about 0.26 cp. So you repeat the same thing for the toluene, and that will give you the value of 0.259. Alright, so I think the next step, you can just refer to the step